Very good morning and welcome. In this lecture, we will cover basically the gas-based direct reduction processes. And in this gas-based direct reduction processes, this is the process that we will discuss. And first two processes, that is the Finmet and Circored, are basically based on fluid bed reactor, and the rest of the processes all are based on SAT furnace. Okay. And the Midrex process I have separated because it is the widely used process, and in India has several units. Okay. So, Finmet process, first I will discuss with the Finmet process, that is the fluidized bed process. Okay. This is a modification over the fire process. Actually, the fire process was the original process of the fluid bed reactor, and later on, based on the experience on the fire process, this Finmet process has evolved. The plants, Finmet plants was built in Orinoco plant at Puerto Ordaz in Venezuela. As you know, Venezuela is a gas-rich country, so they have a lot of natural gas resources. So they ventured in the gas-based process like Finmet initially. And they had basically 2 units of 1 million ton per annum each. That was the originally built in the Orinoco plant at Venezuela. And then another plant was established in Australia, that is called the BHP HYL-I plant at Port of Hedland. And this has a capacity of around 2 million ton. So this was also 2 million ton capacity was built, but later on it was stopped, and because of an accident. I will talk about that. So features, if you see, then the reformed gas is enriched in hydrogen by applying the CO shift reaction and the CO2 removal. First of all, if you want to see this process, let us look in this process schedule. First, this is the natural gas and air. Basically here you give, and some natural gas you have to burn basically to supply the heat for the reformer. That's why here natural gas is burned with air and natural gas is supplied here basically to burn the natural gas to heat the reformer. And the reformer, what you give, there is the steam you give and also the natural gas. So it is a steam reforming. So you do the steam reforming of natural gas, that is the CH4 reacting with the moisture H2O, it will produce CO and H2. And then CO and H2, you just make an CO shift reaction like this, CO plus H2 forming H2 and CO2, such that you can increase the gas enriched in hydrogen. Okay, because from the natural gas reforming, you will get obviously initially 1 mole of CO and 2 mole of hydrogen, and then further you can increase the hydrogen into the reformed gas by CO shift reaction, that is in moisture, in presence of moisture, steam, the CO can react with forming the hydrogen and CO2. So this is called the CO shift reaction. So the gas becomes rich in hydrogen, and hydrogen rich gas is better, as you know, because hydrogen is a better reductant, and also the reaction can be carried out at comparatively lower temperature, and that is beneficial because the fines tends to agglomerate in the operating temperature, it's little higher temperature. Okay, so if you can reduce the operational temperature, then your sticking of these particles, okay, in the fluidized base will be reduced. That was the thing. So CO shift reaction you apply, and then obviously you are increasing the CO2 because of CO shift reaction. So you also take out the CO2. So after taking out the CO2, then the gas become further enriched in the hydrogen. Okay. Then it goes to a reducing gas heater. This is also a gas heater. Here also you burn some amount of natural gas with air to produce the heat. Also you can circulate the off gas after cleaning. You can that is the mix the off gas, and this off gas you burn with the air, and also you make up with the natural gas because whatever the heat generation required. So basically you, in this reducing gas heater, you use the off gas, burn the off gas with air, and also you make up with the natural gas such that the sufficient amount of heat is generated and the gas is preheated And after preheating the gas around 810 to 830 degrees centigrade, you push it to the reactor number 1. And then the gas from the reactor number 1 enters into the reactor number 2, and from reactor number 2 it enters into reactor number 3, and from 3 it pushed to the reactor number 4, and the feed is charged from the reactor number 4. So it is a counter current process. You can see this is the solid is flowing in this 4. There is the fresh solid entered into the R4 and then goes to the R3 and then R2 and then R1. Okay. So this is the way it goes. The feed comes from here. And then finally from the reactor number 4, R1, there is R1, you take out the fines, the metallized fines, and you hot briquette it. After briquettizing, you have around 85.7% metallic iron with 0.5 to 1.5% carbon. Okay, so this is your output you can get. And so this is the schematics. Okay, so in the R1 and R2 reactor, basically your Woods-Tide reduction take place. You can find the Woods-Tide FeO react with the hydrogen forming Fe. Also FeO can react with the carbon monoxide forming the Fe and CO2, and then Fe can react with the carbon dioxide to produce the iron carbide. That means the carbon goes into the basically austenite structure and finally it forms the iron carbide. So carbon contained, there is the carbonization process, so carbon into the iron increases. So R1 and R2 basically Woods-Tide reduction as well as carbonization of the DRI. Okay, and R3 and R4, they are basically higher order oxide get reduced like Fe2O3 to Fe3O4 and Fe3O4 to FeO. So this reaction basically take place both by the CO as well as CO2 as the reducing gas. So this is the process, roughly this is the process. And so feature is reformed gas is enriched in hydrogen, that is the thing, and applying the CO shift reaction and the CO2 removal, and ore and gas preheating by the recycled gas. So one thing is that is if you can enrich the gas with the hydrogen, then as I said, you can carry out the reaction comparatively at lower temperature, so the sticking problem of the particle will be less. Then ore and gas preheating by the recycled gas, that is the recycled gas that is coming, that you can use, that is the thing, that is the gas preheating you can do. Obviously recycled gas goes to the gas preheater, there is the reformed gas preheater, as well as and the feed also, that is you can also preheat the solid with the off gas. Okay, so that basically helps into this thing. Okay, another thing you can find here, there is the beneficiation plant is there is the iron ore, that is the local iron ore fines that contains around 62.5% total iron, 5% silica, 2.4% alumina, quite rich in alumina. And then in the beneficiation plant, basically you can enrich the material to 67.5% iron total, 1.6% SiO2 and 0.6% alumina. Then this can go into the feed. So alumina and silica reduces significantly, then you enter into the feed, and so some preliminary beneficiation is done. So this beneficiation is basically mainly the gravity separation and the magnetic separation. Okay, and after that it goes. Okay, and this ore basically before putting into the reactor you preheat with the recycled gas. This is one modification over the fire process. In the fire process it was not there. Also fire process did not have the CO shift reaction and CO2 removal, this system, and also ore gas preheating by recycling gas was integrated in this process. And the advantages are directly utilizing the beneficiated fines in natural size distribution. That is the thing, whatever the size, you have the original size, and after you beneficiate it, after beneficiation you just charge that feed material without any grinding or anything else. So what was the natural size distribution? You apply the same size distribution without involving any energy intensive process like grinding and all these things. Okay, so directly utilizing beneficiated fines in natural size distribution, and higher strength of the fine based briquettes over the pellet based, because that is the thing, whatever the briquette you get, that is based on the fines get briquetted, and then strength of the briquette become higher than if you just briquette the pellets. Okay, So fine based briquettes are much stronger, so you can transport to a longer distance. Disadvantage is operating with high pressure. There is a 12 atmospheric pressure. This is all the reactor, fluidized bed reactor are at the 12 atmospheric pressure. And to attain the 90% metallization, if you want to attain, it has to be a very high pressure and at temperature of comparatively lower temperature, 850 degrees centigrade. You want to process this with a very high pressure. Well, obviously, at the high pressure, your reaction will move into the forward direction, because all this reaction, okay, so reduction reaction and the high pressure, because the reactant concentration will be high, you can carry out this reaction at a faster pressure. So and also 90% you have to have. So this maintaining this high pressure, okay, for attaining 90% metallization, that is in the reactor, there is the control and the charging, all this become little difficult, operation becomes difficult. Second is that Headland plant shut down in 2004 following an accident. In one of the reactors, they had an accident, possibly because of very high pressure maintenance of this thing. And Ornico plant's productivity also gradually has decreased. There is the Venezuela, that plant also gradually decreased. In 2010, it produced only 0.5 million ton per annum. Okay, so this fluidized bed has some inherent problem. Although very elegant technologies are there in place, but still it has some problem with the high pressure in the reactor, and that's why they are not become very popularized. Otherwise, the fluid bed, in this case, since it is in the fluid state, if there is a sticking problem is another problem. That is, the particle try to sticks and finally they become agglomerates, and then finally the process shut down because the process doesn't work. Okay, they become bigger and then settle down. So this process doesn't become. So this has two inherent problem with this. In spite of all these changes, and some problem still remains, and also maintaining the high pressure because of that. So this problem is there. And then another process is called the Circored process. So in the Circored process, the idea was again that is to reduce the furnace operating temperature such that the fine agglomeration doesn't take place. So here the main idea is to use the hydrogen as the sole reductant. So only hydrogen. Okay. So in this, I will just talk about the process first. So you can see the iron ore fines are first dried. Okay, there is the fines. That is the fines you take. You first dry it, and then heat it to about 800 degrees centigrade in a fluid bed preheated system. That is, before this preheated iron ore comes, there is also a circulating fluid bed system where you just preheat these iron ore fines. Then these fines, dried fines, are then charged into a circulating bed, fluidized bed for reduction, pre-reduction. Okay, this is the circulatory fluid bed. You can see that is the undersize will come through this undersize, and the unreacted product will come through this and will be circulated like this. So fluid bed reactor basically operate at a very high speed, and the solid comes through it, and again it is charged from the bottom. Okay, so unreacted solid is basically put in a cycle so that they can finally get reduced. And CFB basically operation is very short time, that is the 15 to 20 minutes, such that you can get a metallization of around 70%, and then that is fed into a static bed, fluidized bed. Okay. The fines are reduced to about 70% metallization in the CFD. So CFD, that is basically 70% metallization, and then they come to the fluid bed reactor, fixed fluid bed reactor, and the fluid bed reactor is compartmentalized. Number of compartments are there, and the residence times is also quite high, around 3 hours, such that you can reduce it to a very high metallization, about 90%. And the required energy in the CFB comes from, you can see that is the fuel, there is the natural gas and the air that is preheated and then passed into the CFB. So natural gas and so sensible heat along with the natural gas and air plus natural gas burns produce the heat. Besides, the circulation heat is there already, the circulation process gas is in circulation. So that heat is there. Also some sensible heat comes with the preheated iron ore, that also add to the CFB, and that sustain the total CFB operation. The pressure in the CFD is about 4 bars, and the reaction temperature, you can see it is 630, considerably less than your Finmet process. At 850 degree centigrade, here it is 630 degree centigrade, so very less temperature, and it avoids the sticking problem. And it has been possible basically using this CFB, there is some pre-reduction and all these things. Okay, so in the circulating fluid bed, there is a sticking problem completely avoided. As I said, there is the retention time in the CFB relatively short, of the order of 15 to 20 minutes. A portion of the partially metallized fines are withdrawn from the CFB and enter into the fluid bed reactor. So then they enter into the fluid bed reactor. The fines finally reaches the metallization of 90 to 93% in the fluid bed reactor, as I said. And the products leaves the fluid bed reactor around 663 degrees centigrade and is reheated to 680 degrees centigrade and briquetted. So briquetting requires little more temperature, little soft material. So again, this final product goes through the flash heating, the cyclone, and then it goes to the hot briquetting. Okay, so hot briquetting, and then it is produced hot briquettes. Okay, so the process gas, you can see finally the off gas from the CFB. This is under circulation. After that, the off gas come through it, and after proper cleaning, and this off gas again come here for different heating purpose. So this is the process gas heating is joined at the process gas heating, and also it can go to the fluid bed reactor. Okay, and also the gas from some fresh natural gas and air, preheated natural gas, and also join the fluid bed reactor to sustain the temperature requirement of the fluid bed reactor. So unique feature, it uses the hydrogen as the sole reductant. This is the most important thing, that it uses hydrogen as the sole reductant. Okay, so natural gas is reformed to completely to hydrogen, and low temperature of the reaction, that is only 630 degrees centigrade, and that avoids the sticking problem of the powder particle. No sticking even at high pressure. At 4 atmospheric pressure, you don't have any sticking. And you can see the fluid bed reactor, since it is circulating fluid bed reactor, you can operate at much lower pressure. There is the 4 atmospheric pressure. So that's why if you decrease the pressure, then the operation will become much easier. And no methanation, it has been found, that is because since it is totally reducing gas is hydrogen, no chance of methanation in presence of CO. And product, it is interestingly, this product is free of carbon, because there is no CO, no source of carbon into the reducing gas, because it is purely hydrogen. So the gas is complete DRI, is almost pure iron. Okay, and so that is the thing. But this process also not been very much commercialized. One plant is there still, but it has also not been in full operation. Presently, no circular process is in operation. Okay. So HYL-I process. Now I will move. These are the two processes, major processes. I talked about the fluid bed reactor, fluidized bed reactor, and this process has not got much success, although with a very elegant process technology was developed, but not much of success as far as the commercialization is concerned. Now I will talk about the process that are based on basically SAT furnace, and among these the HYL-III, HYL-IV and the Midrex process are commercially very successful, especially the Midrex process, and I will talk of this process one by one. And first I will start with the HYL-I process. This HYL, basically this name is derived from Hozalota y Lamina SA, and this is termed as HYL SA also, and this is a company based in Mexico, and they first developed this process. And the first plant was installed at Monterrey, Mexico. And you can know Mexico, Venezuela, these are very gas-rich countries, so that's why they invented this type of gas-based processes. And this HYL process, first process, HYL-I process, was initially based on 4 batch reactor, batch shaft reactor. All of the shaft reactor, you can see 4 reactors are used, 3 of them in tandem, and the 1 reactor always on the turn down position, either charging, discharging, and all this. So it is basically set furnace based batch process. This is the batch process because the reactor is filled with that is the charging material, charged as iron ore, and then it gets completely metallized. After that, it is discharged. After that, it is discharged from the bottom. That is, the DRI is discharged from the bottom. That's why it is a batch process, not a continuous process. You charge the iron ore, and after the processing is over, then the DRI is taken out from the bottom. So 3 reactors in line and the 4th reactor in turn down position. This is called the turn down position. That is, either you are discharging, and after discharging you are charging. So charging, discharging take place, and 3 reactors in line, that is, they are getting either preheating or the main reduction and then cooling. All this process goes on this. And the major reducing gas here also come by the steam reforming. So CH4 with the steam, you have some catalyte. There is the steam reforming major catalyte is the nickel catalyte that you have to use it. So catalytic steam reformer is there. And then after you reform the gas, your quench tower is there. Basically, you take out the moisture out of it to make it dry. And after that, this gas goes to a reactor, that is this one of the shaft reactor, where basically the DRI has been completely produced, completely made. Okay. So here the DRI is finished, that is DRI's production is finished. So here the reformed gas entered into that reactor, and this gas is used to cool this, what is that, DRI produced, and in turn it gets preheated. So the gas gets preheated and the cooling of the DRI takes place. Okay. And this gas, obviously, although it is heated, but it contains a lot of moisture from the DRI, it collects a lot of moisture. So this gas requires a dehumidifier. So you take out the moisture from the gas, again you reheat the gas to some extent, and then you pass the gas to the main reduction shaft. This is the main reduction shaft. Okay. So the content of this shaft already preheated and pre-reduced from the previous reactor. Okay. Now the main reduction of this charged material is going on, and the off gas from this main reduction unit, that also undergoes the gas dehumidified and then some gas preheating, and then it goes into the reactor where basically the material has just been charged. So it is a fresh charge is there. So when this gas goes, is basically preheat the charge, and some kind of if possible, some initial reduction also will take place. Okay. After the gas goes to the stack. Okay. So this is the process, and in the next cycle what happens, basically reduction is completed in 3 stages, and each of 3 hours duration. All this process requires around 3 hours, as I said. And the reactor switch is done through automatic valve manipulation. That is, the reactor does not move, only you have the valve manipulation. The reactor are connected with different valves. So now in the first cycle, you can see now the cooling of the DRI is over. So this reactor now ready for discharging. Okay. So this is ready for discharging. So it will first discharge and it will be charged. So it will be converted to the 4th reactor. This is a charging and discharging reactor, and the gas valve will be disconnected with this, and the reformed gas now directly will come to this reactor, and this reactor now become the cooling reactor. Okay. So with valve manipulation, you can take the reformed gas directly into this reactor, so such that the DRI get cooled here, and the off gas from this after dehumidifier gas filter will enter into this reactor. Now this reactor is now the main reactor. Okay. So here the main reduction will take place, and after that gas will go to this reactor. It will not directly go to the flue gas. Now it will go to this reactor, and here its preheating and pre-reduction will take place, and then the gas will go to the stack. So in the next cycle. Okay, so you can see the status of the reactor changes. Okay, so this becomes charging, discharging, discharging, charging reactor. It becomes a main reactor. It becomes the cooling reactor, right? It is charging, discharging. It is become the cooling reactor, and this become the main reduction reactor, and this become the initial preheating and pre-reduction reactor. Okay, so only the valve manipulation is done. Okay, the reactor stays in their position. Okay, so it is under now discharging, and then it will be charged. So this is the way switch. And specific energy consumption is quite high, but around 15 gigajoule per ton of DRI. If you compare it with the blast furnace iron making, that is around 20 gigajoule per ton, and blast furnace product is liquid iron, and here the product is solid iron. So it has to be melted and it has to be purified. So a lot of energy involved is there. So considering that, if you compare 15 gigajoule to 20 gigajoule, this solid iron production here is quite energy intensive. Today, no HYL process is in operation because it requires a lot of time. Each reduction unit takes around 3 hours. Okay, so 3 hours time is required for production, and so productivity is low. And second thing is that's why the energy consumption per ton of DRI is also quite high. So this process is not in operation, and this HYL process, HYL-I process, has been converted to HYL-III process, and HYL-III is in operation, and HYL-III only one continuous shaft reactor is used. So charge is entering in one reactor and going out. So it is only one continuous shaft reactor used. That's why that process become energy economic. It becomes economic with respect to the energy, and productivity is also high. So but in its heydays, in early 1980s, it produced around 40% of the global DRI. So this was the only process, very prominent process in 1980, where it produced around 40% of the global DRI. Okay, so this is about the HYL-I process. Now I will go to the flow sheet for the HYL-III process. HYL-II was marginally modified over the HYL-I and not commercialized. HYL-II process was not commercialized. Then came the HYL-III process. HYL-III is completely a different version. Here the 4 batch reactors are replaced by a single continuous reactor, as I said. You can see here. The steam deforming unit remains as it is. So natural gas is coming, and natural gas, and you can see the fuel, and you are giving the fuel because this is the reheater basically. Okay, it is the reheater fuel you give. This is basically what you see. This shape is the basically steam reformer. So you have to give fuel such that you can supply the heat, and your water is coming. Water, you can see this water is get preheated by this off gas from the reformer. Off gas from the reformer you use to generate the steam out of water, and this steam comes through it, and then also it is get preheated into the reformer, and then it finally joins, the steam joins with the natural gas and goes into the reformer again. There is the reformer again. Okay, so this is the way. There is the better heat utilization. So complete heat utilization you do, and after that your reform gas come out, and you condense the gas to take out the moisture. Okay, and then the dry gas come to the again in a the reducing gas preheater. This is the reducing gas or the reform gas preheater. So here also you can give oil, and then after that this goes to the main reactor. And also that thing is the off gas also, after taking out of the moisture, after making it dry and clean, this off gas also join the is used for supplying the energy into the reform gas preheater. Okay, in this gas. So you fuel gas, you can see this gas also contains CO, so you can burn it and generate heat for gas heating purpose. And after that, gas more than 900 degrees centigrade enters into this reactor. And this reactor you can find, so this shaft reactor you can find it has basically two zones, okay, and in the top you have a high pressure zone, okay. This is a high pressure reactor where the basically reduction take place, and you have at the bottom there is the cooling zone is there, okay. This is the cooling zone is there, and where the basically DRI get cooled, there basically you supply the natural gas, and the natural gas also crack in this portion, in the cooling portion, and it carburize the DRI, okay. So, and this reactor you can see there is the top reactor it operates at a high pressure, and there is the isobaric zone through which this top portion is separated from the bottom portion, and you can independently control the reaction both in the top and the bottom portion of the reactor, okay. So, reforming unit is similar that of the HYL-I. So, some distinctive feature of the HYL-I, there is a natural gas reforming is carried out using steam, as I said, and the partial combustion of the natural gas in the combustion chamber before remote gas inlet allows the reduction chamber in excess of 900 degrees centigrade. Because of the preheating unit, you can gas, there is a reducing gas entered at higher temperature 900, enables the HYL attain to high carbon in the DRI. So, upper high pressure reduction chamber, as I said, is separated by an isobaric zone such that you can independently control the both reactor. Interestingly, that is, you can see there is the process gas is not recycled through the reformer. So, reformer life is more and longer life of the catalyst. Independent reforming section, and since the reforming is totally independent, it does not have any interaction with the process gas. So, you can independently operate it. Energy consumption 9 to 10 gigajoule per ton of DRI. It is quite less than the 15 gigajoule per ton as was in the HYL-I process. Capacity is 0.25 to 2 million ton per annum, and 20 to 30 such plants are there with total capacity of 11 million ton per annum production throughout the world. One of the 0.75 million ton HYL-III plant is in India, that is in Raigad, Maharashtra, Welspun Max Steel, and more flexible with respect to the raw material. You can charge 95% plates, but 100% plate is not possible because they have sticking problems. So, 5% non-sticky iron ore you have to apply. Then you can operate with the 95% platelets, or you can use 80% lumpy ore with 20% plate, that is also possible. So, lumpy ore you can use because the reactor operates at the high pressure. So, some you can compromise with the raw metal to some extent, okay. Okay, now I will close this lecture here, and I will just continue or resume the lecture in a lecture number 56. Okay, I will just take a break now. Thank you very much.